In 3 dimensions, it's possible to not only find the moment around a specific point, but we can find the moment around a specific axis that's not one of our coordinate axes. And this is going to be useful if we want to know around a non-coordinate axis how much of a twisting there is. So for example, if we're trying to tighten a screw or a bolt, then it might be important to know how much of a twisting or how much of a moment is around the longitudinal axis of that bolt or that screw, especially if that bolt or screw is not aligned with the X, Y, or Z axes as we have defined them in our problem. Now we can only do this in 3 dimensions because in 2 dimensions, the only possibility is that we're going to have a moment around the Z axis. But in 3D, as we saw when we took the moment around a point, there's going to be potentially some twisting around the X, the Y, or the Z, and we want to find, when we take the moment about an axis, how much is just along some specific axis. So it's very similar to what we did with forces when we were looking at how much of a force acts along a specified axis or a specified direction. And actually the procedure is going to be similar as well. But we're interested, like with the forces, is how much is parallel to a specific axis. So in this kind of 2-step process of how to find the moment about an axis, we can use these equations. So on the top line, if we want the moment around axis AB, which will be, first we would find the magnitude of the moment around that axis. And we can look at how the notation works here. So we want the moment around axis AB. Notice there's an overline to indicate AB as an axis. We're going to take the moment around any point on that axis. For example, point A would obviously lie on the AB axis, or the moment around point B, which also lays on the AB axis. Or it could be any other point on the AB axis. This is just 2 examples. So take the moment around any point on that axis. It's going to be a vector quantity, and then we dot it with the direction of that axis. So the unit vector that points from A to B. Now notice here, if I'm talking about the AB axis, that is different than the BA axis. It is in the opposite direction. So if the AB axis, I want to use unit vector AB. If it were the BA axis, I would use the unit vector BA. So I'm going to take the moment about any one point on that axis, and that's going to give me a vector quantity. I dot it with the direction. So what have I done there? I've seen how much of that moment lays in the direction of the UAB axis. And just as we saw before, I'm taking a vector, I'm dotting it with another vector, and my output is a scalar quantity. So this gives me the magnitude of the twisting around the AB axis. So again, for example, if AB axis were the axis that passes through a screw, this would be telling us how much torque is going to just tightening that screw. Now, we might want not only the magnitude of the twisting around a specific axis, but actually the vector quantity or the vector representation of that moment about the axis as well. So in the second step, we can take that moment that we just found as a scalar quantity, and now we multiply it by that u hat AB. So we're taking a scalar times a vector, and now we're getting the vector expression for the moment around that AB axis. And again, I want to emphasize that we can use the moment around any point that lay on the AB axis for that moment calculation. So even though the moment about A and the moment around B are different, when we dot them with the direction, they always will give us the same result. Now, alternatively, if you look in the textbooks, it presents another way to find this moment as a one-step process, and they use what's called the scalar triple product to do so. So we can find the magnitude of the moment around the AB axis all in one step. Instead of having to first find the moment around a point and then dotting it with a direction, we can do it all at once here by taking the direction of the axis and dotting it with a cross product. And then we would get this cross product calculation. So notice it is different than when we take the moment around a point. We don't have I, J, and K up in the first row here. We have the components Ux, Uy, Uz of our unit vector instead. So when we do this cross product, we don't have a vector I, J, K, and then the output is not a vector, but it's a scalar quantity. So this is mentioned in the books, but I really recommend that you use the first method instead, where we're going to first use the cross product to find the moment around a point. Then once that step is done, take that vector and then dot it with the direction. So doing it as 2 steps instead is going to be a more reliable method.